morning friends. We will be continuing our discussions on Bode plot. Before we start, I would like to just bring to your notice some small slip that I had made yesterday. I was mentioning about two frequencies, omega n1 and omega n2. If you remember, somebody pointed out later on. What is that? Anyway, it was like this. Omega n1, there was a frequency omega n2. So, what I meant was omega n1 is less than omega n2, and it was in the numerator s squared plus twice zeta 1 omega n1 s plus omega n1 squared divided by s squared plus twice zeta 2 omega n2 s plus omega n2 squared. So, the curve was somewhat like this. Okay. This was omega n2, this was omega n1. Okay. In the phase plot, this was 20 log of g. In the phase plot, we discussed for a function like 1 by s plus omega c, approximately 1/10 of omega c, approximately 1/10 of omega c, the angle was about 6 degrees, minus 6 degrees, and at 10 times this, it is 84 degrees. All right. So, it is close to 0 degree and this is close to 90 degrees. So, almost in 2 decades, you are having a fall of 90 degrees approximately. So, if one draws a line 45 degrees per decade, in many books they write 45 degrees per decade straight line, and this will be slightly over this and slightly below this. Okay. It is 1 decade around omega c. Okay. So, this is again another approximate sketch in the phase. Today, we will be taking up the quadratic form in a little more detail. Suppose Gs equal to 1 by s squared plus as plus b. B is same as omega n squared. It is just the way we write twice zeta omega n. Okay. What will be 20 log of g at s equal to 0 tending to 0? It will be 20 log of 1 by b at omega equal to 0. That means DC value. Okay. At omega very high, omega tending to infinity, it will be 1 by s squared, 1 by omega squared. So, it will be tending to infinity with a slope of 40 dB per decade. So, at omega tending to infinity, 20 log of g will be tending to what? Minus infinity? Minus infinity with a slope of 40 dB per decade, because it is proportional to 1 by s square. It is approximating 1 by s square, 40 dB per decade. When is it maximum? Suppose A is reasonably small. When is it maximum? Let us compute that. So, j omega magnitude is 1 by b minus omega squared plus a omega j, magnitude of this. is it not? I am just putting S equal to j omega equal to 1 by root of b minus omega squared whole squared plus s squared omega squared. Agreed? So, 20 log of g. Now, when is this maximum? This quantity 20 log of g is equal to minus of 20 log of this whole quantity b minus omega squared whole squared plus s squared omega squared, is it not? And to get the maximum value, occurs at say omega p. What is this omega p? You differentiate this with respect to omega and equal to 0. So, if I differentiate the quantity inside the bracket, what do we get? So, d g by d omega equal to 0, that gives me 2 into b minus omega squared into minus 2 omega plus twice omega into s squared equal to 0. So, 2 omega gets cancelled, that gives me if you allow me to write b minus omega squared is equal to s squared by 2. Is that all right? Or omega equal to root over of b minus s squared by 2. We call it omega p. When a is small, this is approximately equal to root b if s squared by 2 is much less than b. That means, for small value of zeta, it is very close to root b. That means omega n basically. Root b means omega n. B is equal to omega n squared, is it not? Natural frequency squared. So, the plot will be this is 40 dB per decade, and this is omega p pretty close to omega n. At this value omega n, how much is this height? So, what is the value of that? 20 log of g at omega n. Omega p is close to omega n. So, if I put just omega n, how much is that? At omega n squared minus omega n squared and b, they will get cancelled. So, it will be just 1 by a omega n, is it not? 1 by b minus omega n squared, which will be 0, plus a omega n j, magnitude of this, which will be equal to 1 by a omega n, and omega n is nothing but root b. So, a root b. Okay, a root b. Sorry, this is 20 log of g. Therefore, at omega n will be minus, because it is in the denominator, 20 log of a root b. Is that all right? What about this starting value for omega tending to 0? This was 20 log of 1 by b, all right. So, how much is this peak? This is 20 log of 1 by b, this one, and this one we have computed is 20 log of a root b minus. That means basically if I put plus, then it is 1 by a root b. Is that all right? So if I subtract from this side, I will get this peak. Okay. So how much is this? I would like to compute. So if I call it MP, something like your overshoot in a transient process, you measure above the reference, that is the steady state value, is it not? So something like overshoot, if I want to measure MP, how much is it? This is 20 log of g. MP will be 20 log of 1 by a root b minus 20 log of 1 by b. So that will be 20 log of this divided by b, so that will be root b by a. Is that all right? This is very important, 20 log of root b by a. Okay. Let us work out one or two simple examples. There is a question that is asked. You are given the dB gain 20 dB 20 log g as this is 40 dB per decade, and this is given as 2. This is 0, this is 6 dB, and this is given as 32 dB. 32 dB. Okay. Determine GS. Mind you, we are making approximate estimates of such functions GS. So let GS be, it's a function of this kind, k by s squared plus as plus b. Is that all right? Let this be GS. Could you suggest from these values 2, omega equal to 2 at DC, that is omega very very small, this is 6, and at the peak it is 32. Can you estimate these A, K, A and B? Yes. How much is B? Approximately, you know?
20 log 1 by b is...
No, B is corresponding to this frequency, omega n is omega p. So B will be 2 squared. B is equal to omega n squared. 4. Agreed? And then at S very very small, it is k by b. 20 log of k by b is 6. 20 log of k by b is 6. So 6 by 20 is 0.3. So k by b is antilog 0.3 is 2. Is it not? See, log of k by b is 6 by 20 is 0.3, that is log of 2. So k by b is 2. So how much is k? 4 into 2, b is 4, we have already computed, so k is 8. Is that all right? Then what do you do? How much is this? Just now we computed how much is the peak? This value 20 log of 1 by a root b. You can calculate from here or you can calculate from here, either way. So 20 log of 1 by a root b is 32. Is that all right? So 20 log of, pardon? k is 8 already calculated.
Maximum value here, earlier we didn't consider k, it was
20 log of, no, that time we are taking 1 by, so if there is a k, 20 log of k will be added. Is that all right? So okay, so 20 log of k by a root b, instead of it was 1 and the maximum was obtained as 20 log of a by g j omega n. This maximum was 1 by a root b. So if there is a k, it will be k by a root b. Okay, instead of 1, if I had k here, then this would have been k by a root b. Okay, so 20 log of k by a root b is equal to 32, which means 32 by 20. So k by a root b is antilog 32 by 20 is 1.6. Okay, if you remove that 1, so antilog of 0.6 is 4, so 40. So k is 8, a is not known, root b is 2 is equal to 40. So how much is a? 1 by 10, 0.1. Is that all right? So what will be the function gs? Therefore gs is 8 by s squared plus 0.1s plus 4, as simple as that. Any question? Let us take another example. Here you are asked to sketch, that's pretty simple, 10 s squared plus 16 divided by s squared plus twice s plus 100. Sketch the gain function. Okay, so our k is 10. Now in the numerator, if I now we will be talking in terms of poles and zeros. So if I call this as omega z squared, that is that omega n that we are referring to natural frequency, in the numerator we will put a subscript z. Okay, z means corresponding to zeros or numerator. It is corresponding to 0 natural frequency, and this will be the natural frequency in the pole. So omega z squared is 16, omega z is 4, omega p squared is similarly 100, or omega p is 10. Is that all right? And here what is zeta for the numerator? Zeta in the numerator function is 0. There is no middle term. Zeta here you can calculate 2 into zeta into 10 is 2. So zeta is 0.1. Okay. For the second one. So you can sketch it like this. At 4, it will be going to infinity, and from there again it will come up at 10. It will be settling somewhere. So you have to specify this value, and this value where it settles. Okay. So, what will be the starting value? This will be the sketch. How much is this? 20 log. When I put s equal to 0, 160 by 100, is it not? So, this starting value 20 log of g at j tending to 0, very small. So, j 0, we call it the DC gain, is 16 by 100 and multiplied by 10. So, 1.6, 20 log 1.6, that is approximately 4 dB. So, this is 4, all right. What about this maximum value when omega equal to 10? Let us compute here the exact value we can compute. Omega equal to 10 means 10 squared minus 10 square plus 16, so minus 84. So, 20 log of g will be 20 log of 10 into 84, and denominator it will be 100 and this one will get cancelled. So, 2 into 10, 20. Is that all right? So, that gives me approximately 20 log of 10 is 20 and 20 log of 42, log of 4 is 0.6, all right. So, it will be slightly more than that. So, approximately 20 into 0.6, about 12. So, approximately 33. So, this is, all these calculations are somewhat approximate, 33. Where will it settle down? Where will it settle down? S tending to infinity will make it s square by s square, 1. So, only 10, 20 log of 10 is 20. So, this one will be 20 dB. Where it will finally settle down. Is that all right? Let us take another example. I hope this will be a challenging one. I am expecting all of you to participate effectively in this problem. You tell me at every stage, you must guide me. This is 1.4, this is 2, this is 3, this is 6, this is 20 dB per decade, this is 40 dB per decade. This is 0. This is a 0 dB line. Now, tell me what will be the function like. Let us estimate Gs. What are the frequencies? There will be some gain k. There is a line that is starting with a slope of 40 dB per decade. So, what will be the nature of the function? Will it be k by s? or ks or k by s squared, as you said, k by s squared, k s squared. It is going up, so k s squared. Thank you very much. And then it was going up like this, and then it takes a bend at 2, s equal to j2. Then 1 plus s by 2 whole squared. There was a rise of 40 dB per decade, and you are bringing it to 0. That means it will be whole squared, is it not? Then 1 plus s by 3. Here you are having a further fall of 20 dB per decade. Then anything else? Nothing else. It continues. Okay. Then how do you identify k? So you have to identify this height. How do you do that? Actually, there are two informations which are redundant. I could have asked for this frequency. I could have asked for this frequency, or I could have asked for this frequency. The question that was given actually had given one excess information, the same information. So you can calculate either from this side or from this side. I have given you the hints. Now tell me. Say 6 divided by 2 is 3. So basically you are going up like this. So what is the increase in this? In octave, 20 dB per decade means 6 dB. So from 0 it will rise by 6 dB. Is it not? Or from 3, if I double the frequency 3 to 6, it is having a fall of 6 dB. So this height is 6. So is this, because this is a horizontal line. I could have asked you what would be the frequency here. Okay. Suppose this is omega 1. What is omega 1? The question is, what is omega 1? What is omega 1? So 2 by omega 1 is a fall of 6 dB. In a line of 40 dB per decade, that means 12 dB per decade. Alright. So 2 by omega 1 to the power n should correspond to how much? 40 dB per decade is corresponding to n is equal to 2. Is it not? So what would be omega 1? N is 2, is it not? So 2 by omega 1 to the power 2 is equal to 20 log, if you take, is equal to 12 dB per octave. See, per octave means 2 to 1. If I go from 2 to 1, there is a jump of 12 dB. Alright. So 2 to what value? If I go, I will have a jump of 6. It's the geometric mean of 2 and 1, is it not? So you are in the middle, in the logarithmic scale. Equal distance means basically it is a ratio, it's a geometric mean. So it will be root 2 times less, that means 1 by root 2 of 2. So it will be root 2, 1.41. Okay. So how much is k now? We know this is 6. So 20 log of k, 20 log of k. So at 1 it is how much? At omega equal to 1, how much is this? Minus 6, because it is 12 dB per decade, 12 dB per octave. 40 dB per decade means 12 dB per octave. That means 2 to half of this frequency. If I go 2 by 2 is 1, at 1 it will be 6 dB minus, then only it will be minus 6 plus 6, this total height is 12 dB. So, at omega equal to 1 it is minus 6 dB, all right. Normally when we compute these are all asymptotes. So, at a very small value of s, this does not figure, this does not figure. So, it is k a squared. Had it been only a squared, it would have started like this. At 1 it would be 12 dB per octave or 40 dB per decade, is it not? Now, this has gone down by 6, it is here at omega equal to 1 it is 6, actually otherwise it would have been much above this. This would have taken place much later, not at 6, but this has been pushed down by 6 dB, and instead of hitting at omega equal to 1, it is hitting 0 at 1.4. It has been pushed down by how much? 6 dB. So, 20 log of k is minus 6. So, how much is k? Half. So, the desired function is half of k equal to half. So, I write half of s squared into 1 plus s by 2 whole squared into 1 plus s by 3. So, from the sketch of the asymptotes, you are asked to find out, identify GS. Let us take up another example. I am asked to compute GS this is given as 12, this is given as 6, this is given as 7 dB, this is settling at minus 12. Okay. Estimate GS. So, we can write GS as some k times, say a squared plus as plus b by a squared plus cs plus d. Okay. This is, if you remember, in the last class we were discussing about omega n1 and omega n2. So, similarly there are two such peaks, one in the numerator, one in the denominator will come. So, a squared plus as plus b. Now, tell me, in the numerator function a squared plus as plus b, here it is tending to infinity. So, how much is a? The numerator will correspond to the one where the peak goes in the negative direction. This is corresponding to the denominator function. So, for this function, if it is tending to infinity, the middle term will be a will be 0, zeta is 0, is it not? So, it will be a squared plus, this is not there, b, and how much is b? 12 squared, 144, this frequency squared divided by a squared plus cs plus how much is d? Approximately 6, 36, 6 squared. Okay. How much is this height above the reference from the earlier value? How much is the peak? 7 dB is equal to how much? 20 log, we calculated root d by c. Is it not? This is what we saw some time back, root d by c. Remember, root b by a, 20 log root b by a was this peak MP, where it was in the denominator. So, 20 log root d by c, how much is that? 20 log of root over of d means 6 by c. So, from there c, if you compute 7 by 20, so it will be approximately 0.35, antilog 0.35. Okay, 6 by c is antilog 7 by 20, so 0.35 antilog 0.35. Hence you can calculate c. I have calculated c approximately equal to 2.69 or so. It may be wrong, I mean it is somewhat some gross approximations I made. So, once you know c, now what is to be calculated is k. When s tends to infinity, this will be 1, so 20 log of k, and that is equal to minus 12, is it not? As s tends to infinity, so 20 log of k is minus 12, so k is approximately 0.4. Is that all right? So, you know all the values. So far we have studied the variation of the gain with frequency in terms of the asymptotes. This will be useful for estimating the frequency response for a given function. Now, we will introduce the concept of poles and zeros of a network function. Any function, say it may be zs, it may be ys, okay, or maybe transfer function v2 by vs, v2 by v1 and so on, or transfer impedance, transfer admittance, y12, z12 and so on. It can be any function. We can write as some constant into say s plus a1 into s plus a2 into s plus a3 and so on, divided by s plus b1 into s plus b2 and so on. Okay. Some finite number of factors in the numerator, finite number of factors in the denominator. If you can write like this, then at s equal to minus a1, the function is say zs equal to 0. Similarly, at minus a2 minus a3, zs will be always 0. If we take s equal to minus b1 or minus b2 or minus b3, then zs will be tending to infinity. So, when any function blows up, when it tends to infinity, the corresponding values of s we call them poles. When the function tends to 0, we call those roots as zeros of the function. They may not be so explicitly given, it may be any function, but wherever the function becomes infinity, we call them poles. Wherever the function becomes 0, we call them zeros. So, in the complex S plane, we may have minus a1, a2, a3 and so on. We will show the zeros in the S plane. This is the real axis. If a1, a2, a3 these are positive quantities, then at minus a1, minus a2, minus a3 they will be represented in the negative side, a negative real axis, the function becomes 0. So, we show them by a small circle or a 0. Okay. Similarly, at minus b1, b2, b3, b1 may be here, it may be here, it may be here. So, b1, b2, b3 and so on, the function becomes infinity. So, when the function becomes infinity, the corresponding roots, we call them poles, will be denoted by a cross. So, for a function like this, it will be denoted by zeros and cross like this. It is not necessary that the numerator and the denominator will be in such simple factors, all right. There can be quadratic forms where the roots may be complex. So, if you have, say, in this a function like s squared plus twice zeta omega ns plus omega n squared, then s plus a1 and so on. Similarly, you may have, it is not necessary that you will have only one quadratic, you can have multiple number of quadratics. Similarly, twice zeta, I will write the numerator as omega z. So, omega z corresponding to zeros, that means numerator corresponds to zeros, omega p s plus omega p squared into s plus b1 and so on. Then the roots will be distributed like this. There can be poles here at minus b1, minus b2, minus b3 and so on. There will be also poles corresponding to this quadratic, and if zeta is very small, okay, much less than 1, such that zeta omega p whole squared is less than 4ac, that is 4 into omega p square. That means zeta is less than 1. If zeta is less than 1, then it will be, the roots will be always complex conjugate. Okay. What are the roots? What are the roots? Minus b minus twice zeta omega p plus minus root over twice zeta omega p squared minus 4 omega p square. So, how much is it? 1 minus zeta squared into omega p into 2 outside, okay, into j divided by 2. So, that will be minus zeta omega p plus minus j omega p into 1 minus zeta squared. That means omega p minus zeta into omega p will have some real value and plus minus, say here, the roots will be complex conjugates. Now, you see the real part squared and the imaginary part squared, if I take, that is constant. Real part squared is zeta square omega p square. If you take the imaginary part square, it will be omega p squared into 1 minus zeta square, and that is equal to omega p square. This minus term will get cancelled with this. That means with omega p as the radius, if I draw a semicircle, then for different values of zeta, the roots will be lying on the unit circle, on this semicircle. Okay. So, if I keep on changing zeta only, retaining omega z or omega p, corresponding poles or zeros will be shifting along this. Okay. when zeta is made equal to 1, this term will be 0. So, there will be no imaginary part, only two roots will be, both the roots will be real. So, the roots will be here, there will be two roots here, is it not? So, that time we will get 1 by s plus omega p whole square. Okay. At zeta equal to 1, it will be twice omega p s plus omega p square. Similar will be the behavior for the zeros. So, zeros may be located anywhere, here, maybe here like this, and zeros also may fall on a circle of radius omega z. This was of radius omega p. Zeros, complex zeros may occur here and here on a semicircle of radius omega z. Okay. So, depending on the quadratics that will be given to you, the corresponding natural frequencies, you choose the semicircles, and the roots, the poles and zeros for that particular quadratic will be lying on that semicircle, and they will be appearing in complex conjugate form. There are some situations where we have to investigate the nature of these poles and zeros, their locations and other behavior. Okay. While identifying network functions, especially for studying the realizability of a network function, whether a function can be realized by a network element, set of network elements. If you want to study that, then you have to study the behavior of the poles and zeros, that is the distribution of the roots. Sometimes we are interested in knowing the transient response. How do you compute the transient response of a system if you are given, say, GS? GS is a very general function as k into, okay, k may be say 10 into s plus 2 into s plus 10 divided by s into s plus 8 or into s plus 20. Now, this one standard technique that you already know is to calculate A, B, C by partial fraction analysis. These residues you calculate by simple algebraic method. Multiply this function by s, make s equal to 0, you get a. Similarly, multiply by s plus 8, make s plus 8 equal to 0, and so on. Is there any other approach? Given the pole zero distribution, suppose we have poles zeros like this. Is it possible to find out, these A, B, C, etc.? What is A after all? What is A or what is B? These are the residues that we are computing for this function. If I take any value of s here, what does this vector show? Suppose this is at some z1. This is at minus z1, is it not? So, this is minus z1, this is s. So, what is this vector? What is this vector? No. No, there is no pole. I am taking any value of s. S I am varying along this imaginary axis. All right. Then what does it show me? if I vary S along this, what does it show? Now, for that matter, anywhere if I take, what will be this vector like? This is S. So, minus Z plus this unknown vector x minus Z 1 plus unknown vector x is equal to S. So, how much is the unknown vector? S plus Z 1. All right. So, if I take any S, it need not be on this line, any S, then a distance, this vector connecting minus Z1 and this will give me S plus Z1 vector. All right. Similarly, for a pole P1, if I draw this, what will be this representing? This P1 is basically minus P1, is it not? Suppose it is at minus P1, P1 is a complex quantity, all right, then it will be representing S plus P1 vector. If S plus P1 is a factor, then S equal to minus P1 is the root, all right. So, if this is minus 3 plus 4j, then the factor corresponding to this vector will be giving me S plus 3 minus 4j. If minus 3 plus 4j is this point, then this vector is S plus 3 minus 4j. Okay. Similarly, for this one and so on. Okay. So, in the next class we shall discuss about how to compute these A, B, C, these constants with the help of these phasors or these vectors. Okay. So, we know the location of poles and zeros from the factors, and then we will find out how to compute these residues geometrically. Okay. Thank you very much. Okay, good afternoon friends. We are discussing about poles and zeros, location of poles and zeros and determination of residues. Suppose we have a function zs s plus a1 into s plus a2 divided by s plus b1 into s plus b2. So, this type of function, or maybe s plus b3 also. When we make partial fraction of such functions, it may be just the response function, or when zs is there, if you give an impulse input, then this itself will give you the output function. So, any function of this kind, when we want to measure when we want to calculate the residues, a1, a2, etc., we computed, say a1 we computed like this function zs multiplied by s plus b1, and then evaluate this at s equal to minus b1, is it not? Now, this b1, b2, b3, they can be complex conjugate also. If they are complex conjugate, they should be in pair, conjugate pairs. Okay. So, zs into s plus b1, s evaluated at minus b1, I mean by putting s equal to minus b1, evaluate a1. What does it mean? If I multiply by s plus b1, this will go, zs into s plus b1 means this we are evaluating at s equal to minus b1. So, suppose you are having b1 is here, b2 may be here, okay. a1 may be here, a2 may be its complex conjugate, a1 a2 both could have been real also. Similarly, there can be a3 a4 and so on. So, Zs into s plus b1, when we are evaluating at this point, that means I am placing s at m1 m2 sorry m1 n1 minus m2 n2 will become s squared plus 10 into s squared plus 6 minus 11 into 5 55 s squared, okay. So, that is s to the power 4 plus 10 plus 6 16 s squared minus 55 s squared plus 60. So, that is s to the power 4, is that all right, minus 39 s square plus 60. Now, if you evaluate at s equal to j omega, what will this give you? If I evaluate this at s equal to j omega, omega to the power 4 plus 39 omega squared plus 60. Is it always positive for all values of omega? Yes. So, it is realizable, because power dissipated, if it is negative, what does it physically mean? If the real part is negative, that means if I pass a current, instead of getting heated up, it will be cooling down. Is it possible? I square r is negative means what? It is cooling down, that is not physically possible. So, the real part of the impedance function Zs, the impedance function Zs must be always positive. So, even though we have seen earlier for this example the residues are coming negative, it may not be possible to realize by RC combinations. You may try with LC, it may fail. It may be possible with RLC, all right. So, but it is a realizable function. So, if you find that this test fails, it is not positive throughout for all values of omega, somewhere it is becoming negative, then you can say it is not realizable by passive elements. This is not a network function. Is that all right? So, we will stop here for today. We will continue with this, and a few simple realizations we will see with LC, RC and so on.